Imagine trying to stream a 4K video from the bottom of the ocean. Or imagine coordinating dozens of autonomous underwater vehicles during a search and rescue mission. On land, this would be almost trivial. We would simply use Wi-Fi, fiber optics, or 5G. But underwater, everything changes. The ocean is one of the most hostile communication environments on Earth. Signals disappear, light is absorbed, radio waves die almost instantly, and sound travels slowly. Yet our oceans cover more than 70% of our planet, and we still know remarkably little about them. Today, we'll explore one of the fastest growing fields in photonics, Underwater Optical Wireless Communications, or UOC. Communication underwater has always been a compromise. For decades, we relied primarily on acoustic communication, in other words, sound. Sound traveled for kilometers beneath the sea, making it ideal for submarines and sonar. But there's a surprise. Its bandwidth is incredibly small. Sending high-definition video, real-time sensor data, or coordinating fleets of underwater robots simply isn't possible. What about radio? Radio waves revolutionized wireless communication in air. Unfortunately, seawater is electrically conductive, and conductivity absorbs radio frequency energy almost immediately. Even powerful RS transmitters struggle to communicate beyond a few centimeters, so we are left with one remaining option: light. Optical communication offers something neither acoustics nor radio can provide: gigabit data rates and extremely low latency. Communication distances reaching tens and even hundreds of meters. Its closest thing to underwater Wi-Fi. But using light underwater introduces an entirely new set of challenges. The ocean isn't simply a giant swimming pool. It changes dramatically with depth. Pressure increases, temperature decreases, salinity varies, biological activity rises and falls. Every one of these factors changes how light travels. A communication system that works perfectly near the surface may completely fail only a dozen meters deeper. Understanding the ocean isn't just important, it's essential, because underwater communication isn't designed for a single environment. It's designed for thousands of different oceans, and all behaving differently. The biggest enemy of underwater light is attenuation. Every photon traveling through the water faces two unavoidable threats: absorption and scattering. Absorption removes photon completely. Even energy becomes heat. Scattering changes their direction, sending light away from the receiver. Interestingly, pure water absorbs different colors differently. Red light disappears rapidly. Blue and green wavelengths travel much farther, but seawater isn't pure. It contains algae, organic matter, sediments, microscopic particles. Trying to model every one of these individually would be nearly impossible. Instead, oceanographers discovered something elegant. Most of these optical properties correlate with one measurable biological indicator: chlorophyll A concentration. Rather than tracking dozens of variables, chlorophyll becomes a master parameter describing water clarity, a remarkably powerful simplification. Attenuation isn't simply about losing power. Scattering fundamentally changes the geometry of the optical beam. Imagine shining a light through a fog. The beam becomes wider, weaker, less focused. Exactly the same thing happens underwater. Every scattered photon reduces the amount of useful light reaching the detector. Even when enough power remains, excessive scattering can make communication unreliable. So, successfully underwater optical communications isn't just about generating bright lasers. It's about understanding how water shapes light itself. One might assume chlorophyll is even distributed through the ocean. It isn't. Instead, nature creates something called the deep chlorophyll maximum, DCM, a layer where microscopic phytoplankton become highly concentrated. Why there? Because it's perfectly balanced, enough sunlight from above and enough nutrients from below. This biological sweet spot forms a dense optical barrier inside the water column. Understanding where the layer exists becomes incredibly important for designing communication links, because biology doesn't just affect the marine ecosystem, it affects physics. The depth of chlorophyll maximum changes dramatically depending on the environment. In crystal clear ocean waters, sunlight penetrates deeply. The biological layer forms perhaps 100 meters below the surface, but in nutrient-rich coastal waters, surface biology blocks sunlight much earlier. the chlorophyll maximum rises much closer to the surface. This means two oceans with identical depths may have completely different optical communication performances. Designing underwater networks therefore requires understanding not only physics but marine biology. Not all colors of light survive equally underwater. Blue wavelengths travel farther in deep water. Green performs better in biologically rich environments. Near the surface, one wavelength may dominate hundreds of meters deeper, another becomes optimal. Selecting laser wavelength isn't simply an engineering decision, it's an environmental decision. The ocean itself determines which color survives. Even in perfectly clear water, another invisible phenomenon appears. Optical turbulence, tiny fluctuations in temperature and salinity continuously change the refractive index of seawater. The beam no longer travels along a perfectly straight path. Instead, it twists, bends, distorts. Interestingly, salinity fluctuations often create even stronger turbulence than temperature, and unlike attenuation, this problem cannot be solved simply by increasing the laser power, because the beam itself becomes unstable. The distortions produce something called scintillation. The received optical signal begins flickering randomly, bright, dim, bright again, very much like stars twinkling in the Earth's atmosphere, except underwater. The effect can become even stronger. At certain moments, the received signal falls below the detector's sensitivity. The communication link briefly disappears, even though the laser is still transmitting. These random fades become one of the primary limits of underwater optical communications. Fortunately, there is a surprisingly elegant solution. Instead of trying to stabilize the water, we increase the size of the receiver. A larger optical lens collects many distorted wavefronts simultaneously. Their fluctuations average together. The result is much more stable signal. One simple design change can increase communication distance from roughly 10 meters to well 100. Beam geometry also matters. Plane waves and spherical waves interact differently with ocean turbulence. Small point receivers often benefit from spherical beams, but once a larger collection aperture are reduced, plane waves become significantly more robust. This illustrates an optimal lesson. Communication performance doesn't depend on a single component. It emerges from the interaction between transmitter, channel, and receiver. Every design decision influences the others. Eventually, every photon reaches the detector, but not every detector performs equally. PIN photodiodes offer excellent efficiency and extremely low noise. They are ideal when plenty of optical power reaches the receiver. Avalanche photodiodes take a different approach. They internally amplify every detected photon before electronic processing. This makes an extraordinarily sensitive detector, ideal for deep-water links where only a handful of photons survive the journey. Choosing the detector, unfortunately, depends on one question: how many photons are expected to arrive? Perhaps the most fascinating concept of this presentation isn't the biology itself can improve communication by positioning a transmitter beneath a deep chlorophyll layer. That biological barrier begins filtering sunlight naturally. Ambient optical noise decreases dramatically. Meanwhile, the laser remains visible for the intended receiver. The same biological layer that normally blocks communication can become an optimal shield. Underwater optical communication represents far more than a faster communication system. It opens the possibility of permanent underwater sensor networks, autonomous robotic swarms, deep ocean exploration, environmental monitoring. The ocean remains Earth's great frontier. Understanding them requires better communication. A better communication begins with light. Thank you for watching.